Hi everyone, in this video we look at solving side-side angle triangles. Now, something to note is that two triangles with two equal sides and an equal angle that is not contained by the two known sides are not necessarily congruent. Sometimes side-side angle case may result in two possible triangles, and such case is called the ambiguous. Now, in the next few videos, we're going to be working through some examples, and you'll kind of see when you're given two sides and a non-contained angle between those two sides, you'll see when this ambiguous case arises. And just to kind of clarify, if you are given a triangle and you're told what this angle is, like let's say you're told that this angle is, I don't know, 30 degrees, you're told that this side is 7 units and this side is 8 units, this angle is contained, okay? So because it's contained by the two known, or I guess this angle is contained by the two known sides, we'd say. So this case is side angle side case. Side-side angle results when you have two known sides and the two known sides do not contain this angle. So here we have an angle that is not contained, and this is the side-side angle case. So we have two sides and an angle that is known but not contained between those two sides. And we'll see in a second how this can, or I guess it'll be in the next video. You'll be able to see how this can result in two possible triangles. So if you know, as this reads up here, if you have two triangles and like two triangles that have the same two sides and have it the same non-contained angle, they're not necessarily congruent, which means they're not necessarily the same triangle. And you're going to see why that's true in a second, or in the next video, I suppose. Okay, so the best way to learn about solving side-side angles is just to go through a bunch of different examples. So here it says in problem 1, in triangle ABC, A is equal to 4, B is equal to 10 degrees, and angle A is equal to 30 degrees. So let's go ahead and let us draw this out. So I don't know the length of C, so I'll just draw a line of arbitrary length for side C. And I do, however, know what B is. So let's suppose that this is angle A. So this is angle A, and this is 30 degrees, and that would mean that this is side B, and this would be 10 units here. And we know that A is 4 units. Okay, and another thing that I'm gonna label here is I'm just gonna label the height. Now, the height of the triangle is this dimension here. I can calculate the height, so let's call that h. I know that the sine of 30 degrees is equal to h, the opposite, divided by the hypotenuse, which is 10. So h over 10. So h, the height, is going to be 10 sine 30, which is equal to 5 units. So because sine 30 is a half, so 10 times a half is 5. So this height is 5 units. Now, if I try to draw A, now I know that side A is opposite to angle A. If I try to draw this side, I know that it's shorter than the height. Okay, so no matter how I try to rotate the side A, it never intersects side C. So regardless of how I try to rotate this, and let's just let me draw a dotted line. The dotted line represents all the possible places where like all the possible angles for this for angle C. So this would be angle C, and then angle B would be wherever this red line intersects with side C. So that's angle C, and this would be side C. But as we can see, no matter what angle C is, and these are all the possible values for C, C never intersects, side A never intersects side C, no matter what angle C is. So in this case, there's no possible triangles that exist. So no such triangle exists. No such triangle exists. Now, if we tried, sometimes you won't necessarily draw out the triangle, and you're just gonna, you might be given a question like this, and you might just try to solve it using the sine law. So if we try to solve it using the sine law, well, I know that the sine of A, I'm looking for, I'm given side B, so this would be side B. And I'm looking for angle B. So I know that the sine of A divided by A is equal to the sine of angle B divided by B. So I can actually plug in numbers. I know that A is 30 degrees. So for sine A, I have sine 30 degrees over A, which is 4 units. And I should have written this on this diagram here. So this is 4 units. So I have sine 30 over 4, which is equal to sine of B over side B, which is 10 units. And so if I isolate this equation for sine of B, I get that sine of B is 10 sine 30. 10 sine 30, as we saw from before, is just 5. So I have that sine B is 5 over 4. Now, there's something that should kind of set off an alarm here, is that I know that the sine of an angle is represented by so sine of an angle theta is equal to y over r. Now remember that y is always on the unit circle, on a circle that's centered about the origin. Y is always less than, the absolute value of y is always less than r. So I know that sine theta has to be less than or equal to 1 and greater than or equal to -1. And I should have said that y is always, the magnitude of y is always less than or equal to r, I should have said. So, which means that sine theta is between or is greater than or equal to -1, but less than or equal to +1. And in this case here, sine of B is greater than 1. So we know that there's no value of B such that sine B is 5 over 4. So that should tell us algebraically that no such triangle exists. In the next example, we're told in triangle ABC, side A is equal to 5, B is equal to 10, and angle A is equal to 30. Okay, so let's see what happens in this case when we draw out this triangle. Well, and let's just, okay. So in this case, I've got this angle, which is 30 degrees. This is angle A. This is going to be side C. This would be side B, which is equal to 10 units. Since these are the same numbers as before, except for A is the only value that's different here is A, I can draw out the same diagram. So I had that the height of this triangle was 5 units, and the only thing that's different is side A in this case. In the information that we're given, that is. So if I have if A is 5 units and I'm rotating it and I'm going through all the possible values of angle C, you see that side A only, as you rotate side A, it only intersects C, side C at one point. And it's this point right here. So this is side A, which is 5 units. A is equal to 5 units. And in this case, A only intersects side C when side C is the height. So in this case, there's only one possible triangle. And let me draw out all the possible values of or all the possible rotated values of this side A. So you'll see that this the only case where we get a triangle where side A actually intersects side C is where this is a 90-degree angle, and A is actually equivalent to the height. So if in this case we have only one triangle is possible. Only one triangle is possible. And if we solve this using the problem actually asks to solve triangle ABC. If we solve this, we can just use right angle geometry, because I know that this is a right angle triangle. So I know that this this is angle B. Oh, sorry, that is not angle B. That's angle C. This is angle C because it has to be opposite side C. And then this is angle B. So first off, I know that angle B is equal to 90 degrees. Side C, and I should really write only one triangle is possible, and this is a right angle triangle. This is a right triangle. So side C is going to be, or let's do angle C. Angle C, which I should write as uppercase. No, whoops. Okay, angle C is going to be equal to 90 degrees minus angle A, which is 90 minus 30. So angle C is going to be equal to 60 degrees. And then we want to figure out what side C is. Side C, so side C is going to be equal to 10 squared minus 5 squared, which is equal to 100. Oh, sorry, this should be C squared. C squared is equal to 10 squared minus 5 squared because we're using the Pythagorean theorem. So C squared is equal to 100 minus 25, which is 75. Thus C is equal to root 75. And root 75 we can simplify to 5 root 3. So C is equal to 5 root 3. And we have solved the triangle. At the end of any question where you're asked to solve a triangle, it's generally a good idea to write a therefore statement. So to summarize your answer, and we could say therefore C is equal to 5 root 3 units. Angle C is equal to it was 60 degrees, and angle B was 90 degrees. Now, an important thing to note here is that we could have, since this was a 30, 60, 90 triangle, I didn't really have to use the Pythagorean theorem. I could have just looked at the ratio of the sides. Since this is a 30, 60, 90 triangle, remember that a 30, 60, 90 triangle always has sides in the ratio of 1 to root 3 to 2. So I could have just used this ratio to come up with this side length C. So lastly, and this isn't the last case, it's just going to be the last case that we'll cover in this video, and then in the next video in the series we'll actually cover the ambiguous case. But here we're told in triangle ABC, we have that A is equal to 15, B is equal to 10, and angle A is equal to 30. So in this case, let's draw this out. So again, we have angle A is 30 degrees. This is side C. This is side B, which is equal to 10. And let me just move this, actually. You know what? I'm just going to redraw this for a second. So we'll have, okay. So let's suppose that B is 10. This is angle A, which is 30 degrees. This is side C, all the possible values for C. And side A is 15. So it's got to be longer than side B. So let's say it's about that dimension. So we can see that if we go through all the possible values for C, for angle C, that is, that if we're going to intersect, if A is longer than B, we'll intersect at C at this point. But if we keep rotating this side, and I'll try to keep it the same length here, there's only one triangle that's possible, and it's where A intersects, side A intersects C at this point. Okay, so there's only one possible triangle. There's only one possible triangle. And notice that in this case, if we figured out what the height was, A is clearly greater than the height. And A is greater than B. And B is greater than the height as well. So A is greater than the height, and A is greater than B as well. And now we can go ahead and we can use sine law to actually solve this triangle. So we know that this is 15 units. So if we use sine law, we know that the let's label this. This is A, C, and this is angle B. So I know that the sine of angle B divided by B is equal to the sine of angle A over A. This is just using the sine law. So I know that sine of B, plugging in numbers, I get sine of B over 10 is equal to sine of A, which is sine 30 degrees over 15. And I can actually multiply both sides of the equation by 10. So I get that sine of B is equal to 10 sine 30. So I'll have 10 sine 30 is 5, which we've seen before. So the height is actually 5 units here. So we have 10 sine 30 over 15, which simplifies to 5 over 15, which is 1/3. So we have sine B is equal to 1/3. We can then take the inverse sine of both sides of the equation to figure out that angle B is approximately, and again, we're just taking the inverse sine of both sides of the equation. We'll do the inverse sine of 1/3. And we get 19.5 degrees. That means that angle C, so angle C is equal to 180 minus 30 degrees minus 19.5 degrees, which is equal to 150 minus 19.5 is 130.5 degrees. So angle C is 130.5 degrees. Okay, so the next thing we're going to do is we are going to have to solve for side C. And I'm just going to, just to clear some space, I'm just going to erase this diagram that I had drawn here. So to figure out what side C is, we know that that the side C divided by sine of C is equal to side A divided by sine of A. So I know that C over sine of 130 degrees, or sorry, 130.5 degrees is equal to A, which is A is 15. So we have 15 over sine 30. And thus C is equal to 15 sine 130.5 degrees over sine 30. Do this on your calculator, and what you'll find is that C is approximately, let's see here, 15 sine 30, 15 sine 130.5 divided by sine 30. You get 22.8 approximately, so 22.8 units. We have to write a therefore statement, so therefore angle B is equal to, or is approximately 19.5 degrees. Angle C is approximately 22, angle C is approximately 130.5 degrees. And side C is approximately 22.8 units.